All right, engineers, in this video, I'm going to go through an example doing an energy balance for a closed system. So in this example, we have a piston cylinder device shown here on the left, and I'm adding some heat to it. So I'm doing some sort of process to it, and I'm expanding that gas from 1 liter to 3 liters and raising up those bricks. So bringing those bricks up from 1 liters up to 3 liters. And to do that, I probably needed to add some energy to the system. And in this case, I'm going to assume I added some heat to make that happen. So let's talk through how to work this problem out. So it says, how much did the energy of the bricks change? This is kind of a disguised question. What's really asking is, how much work did my device do? And we know that the moving boundary work output for a piston cylinder device, these bricks are constant force, and it's a constant area cylinder, so it's a constant pressure system. For an isobaric system, it's going to be the pressure times the change in volume. And so I can solve this out. I can say that the pressure is equal to 10,000 pascals, 10 kilopascals, that was given right here. And the change in volume, I had going from 1 liter, or 0.001 meters cubed, to 3 liters, 0.003 meters cubed. My change in volume is going to be 0.002 meters cubed. And so if I multiply those two things together, I get my work output. We said that pressure times volume gives me a unit of energy in a previous video. So the work output from this device is going to be equal to 20 joules. That's my work output. So I could solve that part of the problem. That's how much the work output, that work went out of the device and into those bricks. It raised the potential energy of those bricks by 20 joules. The next question, how does the temperature compare before and after the bricks were raised? I'm going to show you two ways to do this. We can actually calculate this mathematically, but I find that it's always easier to draw this out. I like to draw out a PV diagram, PV, and I always like to draw some isotherms, some just cartoon isotherms. So this is the low temperature isotherm, and this would be a higher temperature isotherm, and think through my process on this cartoon. So I started over here at state 1, which was 10 kilopascals and 1 liter, and I expanded that at constant pressure. That was an isobaric process. Here's state 2. That was 10 kilopascals and 3 liters. And so I can see that I went from a lower temperature to a higher temperature. My temperature increased. And I didn't have to do any math to figure that out. I can actually figure out the second temperature. We know from the ideal gas law, PV equals mRT, where this is the gas constant. I can actually look this up for air. I have air. The gas constant is 0.2870 kilojoules per kilogram Kelvin. This table's from the NCEES FE handbook. And I can plug this in, but I don't even need it because I know that this is an isobaric process. So I can rearrange this by pressure is equal to mRT divided by the volume, or because this is constant, that the temperature at state 1 and the volume at state 2 is equal to mRT2 over V2, right? And these values are constant. The mass is closed system, so the mass shouldn't change. R is a constant, it shouldn't change. And so I know that T1 over V1 equals T2 over V2, or that the ratio of the volumes should be equal to the ratio of the temperatures. And since I know the ratio of the volumes, I know my initial temperature was given up here to be 300 degrees Kelvin, I could get my second temperature. My second temperature, T2, is going to be equal to 900 degrees Kelvin. Drawing this picture out is useful. It's also kind of useful. I often do a table of my states, and so I'll have my state 1, my state 2, and and I'll list out my variables. So I have my pressure at 1 is 10 kilopascals, my volume at 1 is 1 liter, my temperature at 1 is 300 degrees Kelvin, my temperature at 2 is 900 degrees Kelvin, my volume at 2 is equal to 3 liters, and my pressure at 2 is equal to 10 kilopascals. So I often will make that table. The other thing that might be useful is I could solve for the mass. We know that the mass is constant. And again, I would just use this ideal gas law. I know the pressure, the volume, the temperature, and I know the ideal gas constant. So using either of these states, I can solve for the mass. And the mass is going to be 0.116 grams. And that would be the same. It's a closed system. The mass isn't changing. That'd be same for both states, 0.116 grams. Next question asks, what is the efficiency of this device? So we can solve this one. Sorry, I skipped ahead. Not what is the efficiency of the device. How much heat was added? I'm going to write out my energy balance here. So we know that for a closed system, Q in minus Q out plus work in minus work out is equal to the change in internal energy, delta U. And since this is air, an ideal gas, we know that delta U is equal to mCv delta T. This is something that tricks people a lot, trips up people a lot, is I always use the specific heat at constant volume to estimate delta U. So when I'm looking at this table, even though this is a constant pressure device, I always use every time the specific heat at constant volume to estimate delta U. Delta U is equal to mCv delta T, always. All right. So we can solve this problem. We know that our workout, we calculated the workout to be 20 joules. We know that there's not work in, there's work out. So I'm going to say that there's no work in, that's 0. There's no heat out, we have heat in. And so we have Q in minus 20 joules, that's my workout, equals mCv delta T. Q in is equal to mCv delta T plus 20 joules. And so this makes it pretty obvious here that we need more than 20 joules of heat added, because some of our heat is going into the internal energy of that system, and some of that heat is going to the work output of that system. And so I need more than 20 joules of heat in to do 20 joules of heat of work output. If I wanted to calculate exactly how much, I could use this value for the specific heat at constant pressure, 0.718. I've calculated the mass, and I know my change in temperature is 600 degrees Kelvin. And so I can actually calculate this out. This value ends up being 50 joules of heat goes to internal energy plus 20 joules of heat goes to my workout. So my Q in is going to be 70 joules. Last part of this energy balance, we're often curious about what the efficiency of this device is. So I always like to think about the efficiency as what I want divided by what I pay. And in this case, I want workout, and I'm paying heat. I'm using coal or wood or some sort of heat source to get that workout. So my workout was 20 joules, and my heat in was 70 joules. So the efficiency of this device is about 29%. 29% of my heat in went to workout. The rest of it was stored as internal energy. So hopefully that video was helpful, working through all those parts of an energy balance, quantifying all those different parts of where the energy comes and goes in a very simple system.